We begin at the obvious spot with question number 1, which is technically a question about motion in space. I say technically because what we're dealing with here is a particle moving along a curve defined by a vector function r of t with components 0, 10t, and 25t minus 5t squared. And sure, that's a three-dimensional vector function, which means technically the curve it traces out is a space curve. But it isn't really. Because that x component is 0, that means what we've really got here is motion in a plane. This is really a plane curve. The only difference between the plane curves that we saw in class, which were typically the graphs of two-dimensional vector functions, so that the z component, by implication, would be 0. In this case, it's the x component that's 0. So this isn't a curve moving in the xy plane, which is what we usually have. It's motion in the yz plane instead. That doesn't really affect how we do the problem, but it is useful in many cases to be aware visually of generally what's happening with the vectors in the problem. Okay, so that being said, well, we just want to find some pretty straightforward stuff here. The velocity vector function v of t, the speed function, the scalar function v of t, the acceleration vector function a of t, and the curvature kappa of t. And it will make complete sense to do those in exactly that order. So to start with, to find the velocity function, well, we're going to use a very familiar relationship that we've seen all the way back to the start of differential calculus, all the way back to Math 1000, which is that velocity is the derivative of position. And the nice thing about vector functions is that taking their derivative just means taking the derivative of each of the individual component functions. So the velocity vector function here, the derivative of r, that's going to be the vector comprised of the derivative of 0, which of course is 0, the derivative of 10t, which is the constant 10, and the derivative of 25t minus 5t squared, which is 25 minus 10t. And there we go. One question answered. Now, to get the speed function, well, that's the scalar function that represents the norm, or the magnitude, of the velocity. So v of t as a scalar, not written as a vector, is the norm of v of t written as a vector. And since we already know what that vector function is, well, its norm is just the square root of the sum of the squares of the individual components. So in other words, that's the square root of 0 squared plus 10 squared plus 25 minus 10t all squared. And that just leaves us with a little bit of algebra. The 0 squared goes away. Let's see, 10 squared, of course, that's 100. 25 squared is 625. 25 times 10t twice would give us a minus 500t, and then plus a 100t squared. So we can simplify that a bit. We'll get 100t squared minus 500t plus 725. And let's see, 25 is a common factor there. So let's get rid of that. Simplify this a little bit. Of course, if we factor 25 outside of the square root, that will leave us with 5. So we'll have 5 outside of, let's see, 25 from 100 would leave us with 4t squared. 25 from 500 would be a minus 20t. And 25 from 725 would be 29. So the speed function is 5 times the square root of 4t squared minus 20t plus 29. Next up, the acceleration. Well, acceleration, again, going back to early differential calculus, that's the derivative of velocity, and therefore the second derivative of position. So going back to the velocity vector that we found as the first part of this problem, and taking the derivative of each of its component functions, we'll get the vector where the first component is the derivative of 0 again, so still 0. Second component is the derivative of 10, also 0. And the third component is the derivative of 25 minus 10t, which is minus 10. All right, that just leaves us with the curvature. Now, here we do have a little bit of a decision to make, because we explored a couple of different formulas for curvature in class. Really, we showed that inherently it's most straightforwardly defined as a formula in terms of arc length, but we don't want to go through and find the arc length function and compose an arc length parameterization. In this case, there's no guarantee that that's going to be at all a workable function. So we'll set that option aside. The second way we defined curvature, and this was curvature as a function of t, which is explicitly what we're looking for here, was to write it as the norm of t prime, where t is the capital T prime, I should say, where capital T is the unit tangent vector, divided by the norm of r prime. And now the norm of r prime we've already got, because r prime is our velocity, the norm of r prime then is the speed we've already calculated. But in order to get the derivative of the unit tangent vector, well, of course, we'd have to find the unit tangent vector first. And since the unit tangent vector is r prime divided by its own norm, so in this case, that's the velocity vector function divided by the speed function, we can see that's not a terribly pleasant function. Yeah, the first component is 0, which is pretty awesome. But the second component then is going to be 10 divided by 5 root 4t squared minus 20t plus 29. And sure, you can simplify the 10 over 5 into a 2. That's still a pretty ugly square root function in the denominator. And then even worse is the third component, where we'd have, after we simplify cancel out the factor of 5, we'd have 5 minus 2t divided by the square root of, again, 4t squared minus 20t plus 29. So that's not a particularly lovely thing. We'd have to divide that by, so there's our unit tangent vector. We'd have to differentiate that, which is going to be even less pleasant, especially that third component. And then we'd have to take the norm of that. And while that may be feasible, that seems like an awful lot of work. That first version of curvature is something you would use in particular if you've already found the unit tangent vector. If the problem has guided you to already get that, then chances are that's the easier way to compute curvature. But that's not the way this problem has gone at all. Instead, the other way of computing curvature is to write kappa as the norm of r prime crossed with r double prime divided by the norm of r prime cubed. And as we said, we've already got r prime, that's the velocity. We've already got the norm of r prime, that's the speed. And our double prime, well, that's our acceleration. So in this context, really, that's just the norm of the vector v of t crossed with a of t divided by the speed function v of t all cubed. Well, that means that really all we need to do to get this curvature is to compute a cross product and then take its norm. That seems much more straightforward than finding the unit tangent vector and its derivative and its norm, especially given that we can already see that that's probably not going to be a lovely expression. So let's see then. V of t crossed with a of t. Well, I'll set this up as a determinant, but if you're more used to just using the formula for each of the components, that's fine too. So I'll put the 3 unit vectors I, j, and k across the top. The components of v then are 0, 10, and 25 minus 10t. And the components of the acceleration are 0, 0, and negative 10. And the fact that we've got all those zeros, especially along the bottom row, tells us that this is not going to be a terribly difficult calculation. The x component, so the thing that multiplies I, the unit vector I, is going to be, let's see, 10 times minus 10 is minus 100, minus 0. So that's just minus 100. Then, in expanding the determinant, we'd have minus j times 0 minus 0 is 0. So the y component is 0. Plus k times 0 minus 0 again. So the z component of this cross product is also 0. So v crossed with a is just the vector minus 100, 0, 0. And that's lovely because then it makes computing the norm there really easy. That's just going to be the square root of minus 100 squared plus 0 squared plus 0 squared, which of course is just positive 100. So then, our curvature is going to be 100 divided by the speed cubed, and so that's going to be 5 cubed, which is 125, times that square root cubed. So that's going to be 4t squared minus 20t plus 29 to the 3 over 2. And then I can just do a quick simplification here. 100 divided by 125 is 4 over 5. So that's 4 over 5 times, you can write the rest of it as you can leave it in the denominator or you can write it as a negative exponent. It doesn't matter. So 4 over 5 times 4t squared minus 20t plus 29 to the power of negative 3 over 2. So there we go. Velocity vector function, speed function, acceleration function, and now curvature all computed. One question down, 9 to go. I'll see you in the video for question 2.